Thank you all for attending this session. This session will be presented by Dr. Bhaskar Rimal and his topic, which is IoT device identification using supervised machine learning. Now, Dr. Bhaskar Rimal is an assistant professor of computer and cyber sciences at the BCom College of Computer and Cyber Sciences at Dakota State University, which is at Madison, South Dakota. He was a visiting scholar with the Department of Computer Science, Carnegie Mellon University, Pittsburgh, Pennsylvania. He was also a postdoctoral fellow with the Department of Electrical and Computer Engineering at the University of New Mexico. He was a visiting assistant professor and academic specialist at the Department of Computer Science at Tennessee Tech University at Cookeville. He's a senior member of both IEEE and ACM. Dr. Rimal, the floor is yours.
Thank you. Can I share my slides? Okay. Can you see my screen?
Yeah, we can see your screen.
Okay.
Yes.
Perfect. Thank you. Thank you for the introduction and thank you for joining me. So today, I'm going to basically talk about Internet of Things device identification, right? It's a, a broad topic, but I will, narrow down the context, right? And how we are using machine learning to detect, IoT devices, especially for its attribution and identification, right? It's a very important topic, and there are so many issues within this topic. We have been working in this area since multiple years, and we have a couple of good, outcomes from this project. So I would like to share some of the outcomes today. So even though it's a huge area, so I hope you'll enjoy this talk. So I'm going to talk about little bit myself, right, and about my institution, DSU. And then I'm going to provide you a brief overview of Internet of Things, before, diving into the topic. We should at least know what is IoT and so on, right? And then I will, go through the main topic, the device identification, and then machine learning approaches to solve the issues and how we solve. And our approaches, in multiple sections you see here, like, network traffic collection, feature extraction, data labeling, and so on. So we'll go through those topics in detail, and I will share some of the, testing results and evaluation. And then I will conclude my talk, and we can discuss, potential for the topic and so on, right? So as you already know that my little bit background, so I don't need to repeat the same thing, right? So I'm going to skip these slides here. So research-wise, I have a wide area of interest. For example, I have been working in the area of IoT since multiple years. And cyber physical systems, cyber security is the integral part, of those domains. And then I'm also the expert in the area of wireless communication, especially 5G and 6G. And I have been working in machine learning, intelligent transportation systems, integrated smart grid, and edge computing. So these are my, favorite domain of research these days. And professionally, I have been very active in IEEE and ACM community. And currently, I serve as a technical editor for IEEE NATO, and also associate editor for IEEE Access. And I have been serving senior associate editor for Euraship Journal on Wireless Communication and Networking. And in the past, I served in similar venue, like IEEE Communication Magazine from 2017 to 2020. And there are other couple of, flagship magazine and journals. So another area of service I have been doing like TPC member in IEEE flagship conferences, right? Like IEEE, GlobeCon, IEEE Smart GridCon, and ICC, and so on, other conferences, right? So, and currently, my research project are funded by the National Security Agency, NSA, National Science Foundation, and the state of South Dakota, right? And I am the director of Patriot Lab at DSU, and you can see the nice building here. Images a medicine cyber lab, so we call it Mad Lab, and within that Mad Lab we have around 16 lab units, and one of them is my lab. So I have been supervising a lot of doctoral students, master's student and undergraduate students. They work for me in my research projects in my lab. And teaching wise, I am the core faculty of PhD program, and so I mostly teach only PhD courses, and sometimes I teach only a few courses in the master's level. And about DSU, some of you may be familiar with DSU. It's we are quite, we are the neighbor, right? Neighboring state. So especially DSU is a small university, but it's a very powerful, university in terms of, STEAM and cybersecurity, right? That's why State Board of Regents is recognized DSU as a STEAM university, and especially for computing, information technology, and cybersecurity. And nationally, DSU is leading several interesting cybersecurity and programs, and it has a lot of values. So for example, here all of our program has has recognized by the as a academic excellence designation, right, from National Security Agency, NSA, and Department of Homeland Security. That's a very important recognition. So we got the 3 recognitions since I think 2012. It has been decade. So Center for Academic Excellence in Cyber Research. So, and then next one is Center for Academic Excellence in Cyber Defense. And then Center for Academic Excellence in Cyber Operations. So what does that mean, right? So we do a lot of research in cybersecurity, right? And that recognition is very important for us. And we operate, cybersecurity related, curriculums and programs, right? And for example, here, from my college, or you can call it department, we call it Beacon College of Computer and Cyber Sciences, where I have listed a couple of program here. Especially you'll see almost all related to cyber program, right? So currently, we have been offering a doctoral program in cyber defense and cyber operations, computer science, right? And other certification and other programs are here. If you are interested, go through the DSU website and you'll find those things. I don't need to explain all of them, right? That's not the intention of this talk, but it's still, I want to give you, kind of brief overview. Okay. So, what is IoT, right? That's the big questions for all of you, right, today. So because I'll be, talking more on technical side of IoT, so I would like to give you some, broad overview. So IoT term is Internet of Things is not new, right? It's back 90s era, it was there, right? And a computer scientist, Kevin, who was a fellow in the MIT, coined the term this Internet of Things, right? And since then, Internet of Things have become these days so popular, right? And as shown in diagram, is connecting everything, right? So no matter where you are, right? Maybe at home or office or I got background noise. So okay. So IoT, right? So IoT describes the network of physical objects, right? As shown in diagram here, or the things in abstract things, right? Anything, right? And that are embedded with sensors, tiny sensors, software, and other technology, right? For the purpose of connecting and more generally, the exchanging the messages, right, among devices and the system over the internet. That's the typical generic definition of IoT, right? And it has a wide range of application you can find in daily basis, right, from your home to your office, enterprise, everywhere, right? So, and some of the use case you can think of, like automotive industry, manufacturing, transportation, logistic, retail, and public sector and healthcare, right? And there are so many other industry, right, where you can see the application of IoT, right? So saying that IoT becomes a kind of pervasive technology, right? So and in nutshell, what I can tell you, like in the hyper connected world, right? Especially connecting tiny sensors, billions of sensors, and that's the hyper connected world, right? And the digital systems, right, that can record data, monitor data, right, and adjust the interaction between connected things, right? And where the physical world meets the digital world, right? That's the foundation of IoT. And they cooperate, right? Digital world and the physical world, they cooperate and they exchange data, they connect to each other, right? And they make a huge system, right? That's why IoT is so important, right? So it becomes a kind of de facto technology for us, for from no matter whether are you technical people or non-technical people, in consumer side, in production side, in research, everywhere you can see IoT, right? From city level, smart cities level, to highly automated, highly precision, agriculture and robotics and so on, right? So that's the IoT. Okay, so IoT, means there's a lot of connectivity, right? Massive connectivity. So, and let's see some of the statistics. Let's review some of the statistics to give you why IoT matters, right? For example, here I have recent data from World Economic Forum. So they have published a very nice report where they mentioned that by 2015, 2025, it's coming, right? It's quite near. So 41.6 billion devices will be capturing data, right? It's huge, right? It's almost high, even 7 times greater the population of the universe, right? So wherever you go, whatever you do, you will be tracked, right? You can be connected through all IoT, right? And it's a massive connectivity. So it's not the surprising data for me, 41.6 billion or around 42 billions of devices connect. It's not the surprising data. If you count digital devices at your home, if you have, 4 members at home, maybe you have more than 20 or 30, even around 50, tiny devices, right? Connected to at your home network, right? And if you multiply the, all universal population, it is, it's the realistic, right? So it's the realistic. So if the, if the internet penetration becomes 100% worldwide, right? That's not a surprising data to me. And, business-wise, so IoT has created a lot of business value, right? And from, automation to maintenance, right? And it is expected that the growth will be, around 16%, more than 16%, right? And that comes with, 263 billions dollar, right? By 2027, right? Is a huge market for, corporate industry, right? So that's, good news for, industry people who, work on those automation and, on those sectors, right? And that's why, IoT becomes so, interesting and so much important, right? And okay, here is another, nice results I would like to share with you. So it's a very recent, and so this data, especially this graph, shows the importance of IoT. Right? So the role of IoT is very become very important, especially in this COVID-19 pandemic. Right, and in the graph you see the projection, pre-COVID-19 projection is the down, and projection impact of IoT exceed that projection, right? So in pandemic, in COVID-19 era, a lot of people use IoT devices. IoT application has been used, for contact tracing and gathering data. This is one of the kind of milestone for IoT researcher or corporation to rethink. Maybe and according to GSMA, they think that most of the enterprise will increase their investment in the automation, right, to improve agility. In the face of future pandemics, maybe another pandemic will come, and how we can fight with that pandemic with IoT, right? And that's the big issue for all of us, right? How effectively we can utilize our technology, right? And that's why as beyond normal healthcare, in healthcare, you have seen a lot of IoT gadgets. So beyond healthcare, in normal condition, IoT has helped a lot for COVID cases, especially for supply chain, automated activity in warehouse and factory, So that means it has a social value as well. Right? That's not only the business value, not only the technical side, right? So that's the typical IoT. So every technology comes with issues, challenges, right? And as a researcher, you may think, hey, what are the risks? What are the challenges over there, right? So whenever you have, in the IoT networks, as is an open network, right? And whenever the devices will be increasing, and there will be always potential cyber attack, right? And cyber attacks is growing, rapidly in IoT, networks, right? And how to prevent from the cyber attack, right? There are different type of cyber attacks, right? And hackers always try to, attack, right, to try to grab your data, right, and or disrupt the network, right, and there are so many things they can do, right. And that's the more challenging part for IoT, because it's a very complex network, huge network, right. Millions and billions of connectivity is there, right. And how to mitigate that, right? How to timely detect the attack, right? How to prevent the attack, right? That's the huge challenge for IoT network. It's IoT network is different than other networks. So because of because of massive connectivity, right? And another things, IoT technology can be also misused, right? And there is always a risk, right? That risk includes, security, privacy issues, or cybercrime, surveillance, or in public space, or and control of mobility and so on, right? And then cybersecurity threat remains a vital area, right? That's the vital area in the IoT ecosystem. Okay, that's the short overview of IoT and the importance of IoT. Now let's talk about device identification, right? So what is device identification in the IoT, right? So device identification is the systematic process, right? And where we try to map every attributes in the device profile, and we try to uniquely identify its device in the network, right? And for example, here unique device identifier UID may be the device identification, or more device attributes, right, that can be used to uniquely identify devices. For example, in the table, I have shown here a couple of attributes. You can see like MAC address, IP address, and so on, right? So a MAC address, can be used as a unique, device identifier, right? But in the trusted environment only, right? And the MAC address is the universal, right? It's a unique. So, but if the device is not compromised, then that's okay, to have a MAC address as a reference, to identify the device. If the device is compromised, means if the network is compromised with hackers, let's say DDoS attack is phishing in your network, and somehow it will be difficult to even identifying your devices with the MAC address, right? So this is a typical example here in the attribute example in the table. So we'll be using so many things in our research. So like in IoT, I explained that the massive connectivity, right? So because of so many devices, device identification become a fundamental issue, right? In cybersecurity domain. And many services like access control and intrusion detection are built on correctly identified devices, right? And in a trusted environment, it is convenient to use MAC address, right, to identify devices. But what will happen if the scenario is changed with compromised, right? And another thing is MAC address can be easily hooked, right? And then identifying devices based on MAC address from data frame is not reliable solution, right? And we have to think of different type of solutions. So there are other approaches. for device identification. For example, cryptography key-based approaches, right? And machine learning, approaches. So another thing here, we have to note that, many devices are deployed in open environment in the IoT, right? And their, physical security cannot be guaranteed, right? That's the huge challenge for IoT, right? And for example, even we use, let's say, cryptography key-based, approaches, they are vulnerable, to data tampering attacks, right? And there is another issue with this, like key management and the scalability issues when the devices increases in the network, right? And the scalability issues will be there, right? You have to face that. So how to solve that issue, right? So in our research, we try to utilize machine learning, right? Especially we focus on traffic. We study the traffic pattern, we tap the traffic and we analyze the traffic, right? And I will go through all this process. So how we do, right? Here is the process we have been using. So we have basically the 4 essential components, right? We propose, especially machine learning approach, that includes those components like network traffic collection, feature extraction, data labeling, machine learning, right? These are the 4 steps. So I will go through all those steps here. So as shown in the diagram, those steps are in a sequential manner. We do first network traffic collection, and then feature extraction, then we go with labeling process, data labeling process, and then we utilize machine learning, and then we're gonna run our machine learning model, and then we gonna try to identify the devices, right? That's our simple approaches. So let's see some more detail. So in this, research, so we have implemented, supervised machine learning, right? So there are other different approaches, unsupervised, self-supervised, reinforcement learning, and so on, right? But we have chosen supervised machine learning for this, project, where we have selected widely used classifier, especially like decision tree, random forest, logistic regression, and SVM is a support vector mesh, right? So I'll be talking them, all of them, how we're gonna utilize. So before going to that, let's see how we develop our network test bed first, right? So here in the diagram, you see here a couple of layers. You see here is the consumer side, IoT devices in one layer, and then we have layer 2 switches, routers, and layer 3 routers, and tapping devices, right? So and that workstation and so on, right? So basically in testing network, so we have Juniper switches, and then some Wi-Fi routers. And for tapping, especially for network traffic tapping, we have NTAP, right? It's in purple color. If you can identify the color on your side, you can see NTAP there. NTAP is connected with workstation, right? And NTAP can operate with 10, 100 and 1,000 Mbps, and we have also, it supports also gigabit Ethernet, right? And so we have, on the other hand, you see a little bit in the bottom, so what we have Wi-Fi Pineapple, right? And then so here basically Wi-Fi Pineapple is used to facilitate the data labeling process in the network. And the NTAP is the main component here. NTAP is connected to the workstation, right? And we use TCP dump, to collect the network traffic using Ethernet connection, and collected network traffic is stored in PCAP files, right? And that's how we capture the network. We run all those IoT devices, right? Some of them are cameras, some of them are motion sensors and televisions, freeze and so on. I will show you a couple of IoT devices that we have used in this research. So this is a typical test bed that we have been using for our research. And then the next step is after data collection from the traffic, so we have to have a feature extraction, right? That's the procedure we follow. So where so once we capture the traffic from our IoT devices, then we're gonna save in PCAP file, right? And then what should we do with that PCAP file, right? So we have used one open source tool. It's called CIC flow meter, right? It was developed from Canadian University. It's an open source tool, and it was originally designed to identify malicious traffic, that may contain malware. For our research, we have extended this tool, and we make this tool to have more features, and that can help us for our IoT device identification. And this tool supports 76 features from your PCAP files, but we have extended, I think it supports now more than 200 features and something like that. So we have been working this tool, and hopefully we'll be releasing this tool, CIC flow meter in our version, extended version by the December second week or something like that. We have planned for that. So this tool, this updated tool could be very useful for, especially for IoT research, for feature extraction and so on. So here, we use this tool, right, for device identification, and we have a total 76 features that could be extracted from each traffic flow, right, including flow duration, total forward packets, and backward packets, and so on. I will show you typical PCAP files to have better understanding. And in addition to flow features, we have used flow ID, source IP, source port number, destination IP, destination port number, and so on, right? Okay, so the another step is the data labeling, right? So we have control testing environment, right? So means that we can control our network, right? And all the connected IoT devices within that control, subnets within our lab, right? So it's a control environment, and its device MAC address and IP address are recorded, right? And when we capture the traffic, so we have capture all those features, and we have since we have utilized supervised machine learning, right? So we need to have labeled their sets, right? That's very important to facilitate supervised machine learning, right? And for each device connecting to the testing networks, so we have recorded MAC and IP addresses, right? And then each IoT devices is configured and tested to ensure its desired features and service, right, in normal condition. And the IoT devices are put in a testing, right, network for some time, right, some period of time, and the network traffic capture from the network, right, using NTAP or Wi-Fi pineapple, right? And depending on the interface, we have alternative interface. So after testing period, so we have I think 24-hour and so on, right? That's the duration to capture your traffic, and then pick up file will be retrieved, right? And then we use that our version of CIC flow meter to extract features, right, from the pickup file. And okay, here is the data labeling process. So a new field, right? That's the label we have added to CSV file, right? For the for the processing. So especially the narrow features are stored in the CSV file. This is a typical example here. Either you can read or you may able to read some of the field like flow ID, source IP, source port, destination, timestamp is hidden, is and flow duration and so many fields, right? It's more than 76 fields, columns we have, right? And so each device is assigned a unique number, and unique number is used as a label, right, in the CSV file. And the label dataset then created, right, with the help of CSV flow meter. And then after that, here, okay, so here we started to use machine learning, right? After labeling, after creating labeled data set. Without labeled data set, we cannot utilize our supervised machine learning, right? And so among several classifiers, we have utilized decision tree, random forest, logistic regression, support vector machine, right? These are the four widely used classifier, right? And so we have adopted those four classifier, right? And then then we start to train the those classifier, right, with our data sets, right? And here, so we have utilized the features, for example, destination port number, protocols, and those 76 flow features from our tool, right? But we exclude some of the features like flow ID, source IP, source port, destination IP, timestamp, and so on, right? And then we start training our classifier, those four classifier, right? And it's ready for testing, right? And then a new label dataset is passed to the classifier, and then the label will be predicted by the classifier, right? And the predicted label value will be compared with the original value, right? And then we check the accuracy for testing, right? And so on. So that's the a lot of time consuming process when you train data sets, right? And so on. So depending on the size of data and volume of data, right, it may take several days, right, to have your results. So here, so in this slides, so I'm gonna quickly show you, training and testing data set. So we have devices here in the second column. We have used, widely used 13 IoT devices from Amazon Echo to, television, right, and some of the Google Homes and so on, right, and you can see in the other columns like training data sets and testing data sets, right? So we have two type of data sets, training data sets. So as I mentioned here, so we have collected those traffic for 12 hours for the testing period, and we have more than 27,000 TCP sessions that were recorded, right? And the testing data sets, so we also, utilize 24 hours, and we have, more than 74,000, TCP sessions, right? So if you increase that duration, maybe instead of 12 hours and some more thousands of data, then your training process will take more time, right? And you may have different type of results. So yeah, so I need to go to a little bit quickly. So we use a Python program, right? We program using Python, and so we use a Jupyter notebook, right? And then we start taking the noting the accuracy and so on, right? So here, especially we have port classifier, right? We have to know the performance of the classifier, right? So that was done with Jupyter notebook, and each classifier was tested and optimized, right, to achieve the best accuracy for device identification. And this table you see in the middle of the slide, this table shows some of the optimized parameter, right? So classifier in the first column and second column, we have optimized some of the values and attributes, right? So and then in this slide, so you'll see some of the testing dataset results, and testing dataset training and testing dataset results, right? So here some of the notable results. So we got in terms of accuracy, like we have Fujitsu Live Book E-series laptop that obtained the lowest testing accuracy, right? It's a 60% only. And whereas we have Samsung Family Hub smart refrigerator that achieve testing accuracy more than 86%, right? What does that mean? It means 86% of our data is true, right? For Samsung family, means 86% is accuracy is quite good, right? To recognize the devices, right? And here in this slide, so I'm showing here some of the feature selection. So here are some feature selection in the right side. I have listed top 10, right? And their performance, importance, for the one classifier, random forest classifier. So, and in the right side, I have some brief description of those features, right? So here, among them, I'm gonna show you the results of the last one, init for win bytes. So in the next slide, so maybe something. Okay, so here we are interested, in observing the behavior of top 10 features on each device, right? And this figure actually, illustrate the distribution of that particular, parameter, right? And that highlights the number of outliers, median and overall range of those devices, right? And then, so I have only 3 minutes to go. So here are some results, our results out of top 10 features. So and we have a classifier. So here SPM has more accuracy, right? 78%, right? It performs well in terms of our top 10 features. And yeah, so we also compare compares others' works, and we found the reference is listed in the below. You may see later, and here we saw the good results. Our approach produces the very good results when we compare the earlier literature similar approach, right? So that's our outcome, and in the conclusion, so what we can conclude that is, machine learning algorithms are stronger, contenders, right, in solving the problem for device identification. So we proved that, hey, machine learning is essential for, IoT device identification, right? And one of the, results here we have achieved, 78% accuracy, right? With the supervised machine learning. And our research, indicates that CIC flow meter, that even we updated the version, is not only beneficial for, analyzing malicious traffic detection, but also for device identification, right? That's one of the, good, outcomes of the project. So hopefully this tool will be popular in the future, because we need this type of tool, especially for, device identification. And this is our first attempt, to make, open source tool and to contribute something for the, the research community. So for the future work, this is ongoing work. And so we have been working, in the project, and now we enter in the second phase of the project, and we have been utilizing other machine learning approaches, basically, balancing the label data sets for training, how to, generate the better performance, and how optimally, utilize those parameters, and how optimally, develop the tool, right? And these are some of the things we have been doing here. And our research is funded by, National Science Foundation for this project, and National Security Agency, right? National Center for Academic Excellence in Cybersecurity, right? Thank you for listening me. So if you have any questions, just let me know. I don't know how much time I'll have, but feel free to reach out to me if you want to collaborate, and if you have any further questions, here is my email address, right? So yeah, I'm gonna stop now.
Thank you, Dr. Bhaskar, for your presentation. In the interest of time, we can answer one question. After capturing data, do you separate data as per the device type, or is it combined analysis on IoT devices and labeling habits?
So we try both ways. So, once we captured the traffic for the labeling, we went through the, one-shot process, no matter which device is there, right? And another way we classify, for devices. So both way we do.
And a follow-up question to that, do you use a confusion matrix to cross-check the results?
Yes, I haven't shown here, too many results. I have so many results, in these results. So some of the results I cannot show because of, it's not the time to disclose other results because of our nature of projects. It's from NSA, so yeah. So it's not available for public. Yeah, of course we use confusion matrix and so on. We have that. Yeah.
Okay, thank you, Dr. Bhaskar. And we will give you your plaque if you can provide us with your email address, which I think we already have. We will email this plaque to you. Again, thank you for your presentation, and we look forward to working with you. Thank you.
Yeah, thank you very much for this opportunity. And yeah, I would be happy for the collaboration, and let me know, for any, external research and grants, papers, publication. Yeah, thank you.
Thank you, sir. Yeah. And another message for the attendees, just a reminder, if you want to continue with the rest of the session, we have one more session. You can join the webinar link that is in the chat.
Yeah, sure. Thank you.